thing I want to tell you that there is no reaction, there is no mixing, so it's simply the two-phase flow in rock fractures. So why we are doing the hydrogen flow in fractures? Obviously for the underground hydrogen storage. And what is it exactly? So whenever you have the surplus electricity, you convert it to hydrogen and store in the subsurfaces, and when demand is higher, let's say in the winter, and then you take it out and use the energy. So why are we using the underground storage? Because currently the hydrogen is stored, if you are using it above ground, there are all the issues with the safety, and currently most of the times we use the salt caverns, but as we increase, as our energy demands increases, we just don't have enough salt caverns. So the promising solution for now is to use the deep saline aquifers and the depleted gas fields. So these are the potential hydrogen sites from all over the Europe, and these are at different technological readiness level for now. But there are, as far as I know, there are 2 sites where they have actually injected the hydrogen in last October. One is in the Austria and one is in the Belgium. So, and I'm currently working on the project that's related to the site at Loenhout in northern Belgium, where they have this Fluxys, which is natural gas storage company. They have been storing their methane for a few years now, and now they want to use that facility to store the hydrogen. And at the Ghent University, we are doing the lab scale experiment for them. This is our little hydrogen team from Ghent. So we have different projects that involves hydrogen. First is the multiphase flow dynamics. We mostly look at the pore-scale in the fracture media. Then we also look at the geochemical and microbial activity, where we look at the reactions and different microbial activity. And we actually, for the samples that we use for the microbial activity is actually taken from the site itself. And we also have one project where we look at the salt precipitation during the hydrogen injection. But today I'll mostly talk about the multiphase flow. So why fracture media? As I have shown you the different sites for the hydrogen storage, most of them, almost all of them have the porous media, but the site at Loenhout is quite special in terms it's made up of the mud rocks, which is very tight mud rocks, has the matrix permeability and the porosity is very low, so the effective flow is in the fractures. So that's why we are looking at the fracture flows for the hydrogen. And if you look at even if you look at the porous media hydrogen storage, there can be hydrogen leak through the cap rocks through the microfractures. So it's very important we also look at the hydrogen storage flows for the fracture media and not just the porous media. And you will find all the literature recently from the porous media. So my objective here is just to characterize the pore-scale hydrogen-brine flow in the fracture networks. So for that, so this is the sample we got it from the reservoir, which is 100,000 meter deep. But as you can also see these fractures here, but it's very difficult to sample these fractures. So what I do is you drill the sample from the nicer section and introduce the artificial fractures in the lab. So we use just the Brazilian tensile test method, and for the different size of the samples, you can induce the fractures. So this is the 3D rendering of the fracture network that we get from the lab. And also if you see these white dots, these are the pyrites in the sample, and that would be really important for the geochemical activity. As you will see, pyrite will react with the hydrogen, giving the hydrogen sulfide. So this is the experimental setup that we have. I'm doing the unsteady core flood experiments at reservoir conditions, so high pressure, high temperature. So just to make sure that we don't have any dissolution, we use the reactor where we have equilibrated hydrogen and the brine. So first we inject the brine just to have the fully saturated core, and then we do the drainage by displacing brine with the hydrogen, and then again we re-inject the brine to get the immersion and the trapping mechanism.
Excuse me?
Yeah?
What's the dissolution of hydrogen in brine? Should be super smooth, super low.
Yeah, it should be. But I'm not sure about the pressure and the conditions for these pressure and conditions to be sure.
Okay.
Yeah. And when we flow, we use the X-ray CT machines to capture the images and the flow dynamics. So you can see this is the rock, we have the fracture, and you have the two phases flowing in the fracture now. Blue is the brine, and the red is the hydrogen. So how the CT works, just to give you a brief. So I have my sample there, you have the X-ray source, and you have the detector. And when X-rays is just like a CT scan you do in the hospital. So the X-rays passes through your sample, and in the sample you have different density materials, like your brine is different and the hydrogen is different. And depending on that, you will get the signal at the detector and you will get the scans. So I do the two type of scanning here. While I'm flowing the flow, while two phases are flowing, I do the dynamic scanning. And I also do the static scan, which is high quality scans at the end of my flow when the flow is steady. And today I'm showing the results only from the high quality steady flows, because the data is huge for dynamic and we are still processing it. Just to give you how it looks in the real life, it looks really ugly, but just for the students, if you want to build a setup with the hydrogen, there are many factors, because traditionally we do core floods with CO2 or nitrogen. It's a bit easier, but when you are involving pressure with the hydrogen, it gets very difficult. So because of the safety regulations as well, so it took us quite few months to get the setup ready. So if you ever think about working with hydrogen, I would say start soon. Okay, so I'm using 3 different fracture samples. Sample A is the pore-scale sample, which is like very small, 6 millimeter diameter. And sample B and C are the bit core scale samples with 25 millimeter diameter. For sample A, what I'm trying to study, because as I mentioned, the storage facility already stores the natural gas, so it has methane in there. And when you want to put now hydrogen, there will be, so how is it different from the methane behavior? That's what we want to study. So I would like to show you the results for different gases, that's hydrogen, pure hydrogen, hydrogen and methane mixture, and the pure methane as well. So, and in terms of sample B and C, as you have noticed, there is a difference in the aperture. So we would like to see how changing the aperture of the fracture, how it affects the trapping and the drainage behavior. And we have seen in today's lecture, so I don't have to go in details, when you have the flow in the fractures, it's given by the cubic law. It's for the single phase flow though, so you have your fracture permeability. But when you have the multiphase flow, this is the real image from my X-ray CT scan. The bright phase is the brine, and the darker phase is the hydrogen. So you have two phases, they are moving in the fracture. So how is the fluid distribution, how they interact with each other, and what will be the effective permeability? That's the relative permeability which we need for all the upscale modeling. That's given by, that will be decided by the capillary forces and the viscous forces and the viscosity ratio of the two phases. So there are very few experiments that have been done for measuring the relative permeability in the fractures. One I could find in 1990, it's for the air and water, and as you have seen, it's the relative permeability behavior is quite different than the porous media, because because of the changing the roughness and the changing aperture field, there is very high heterogeneity and non-local inertia, which causes the more phase interference, and that's why you get very low relative permeability for the gas phase. So we kind of want to do this kind of measurements for hydrogen at reservoir conditions, and that's okay. So first results are for different gases. As you have seen, these are the flow distributions in the fractures for hydrogen methane 50-50 mixture, and the methane. And you can see here the saturation of the gas with the length of the sample. And we have noticed that as you increase for the methane, we get a little bit higher saturation than hydrogen, which might make sense considering the methane has higher viscosity, and these experiments are done at the same flow rate. But one thing I want to mention is you can see the fluid distribution is kind of very similar. That means we were very happy that we can reproduce the experiments because these were done on different days. But we can see the gas and the fluids are going at the same locations in the fracture, so which was good news for the experiments. Then we look at what's the difference with if you change the capillary number. And it's a bit counterintuitive because if you have seen we have seen higher saturation for lower capillary number for both the cases, hydrogen as well as the methane. What we think for now, the hypothesis is because the time of the experiment would be higher for the low flow rate experiments, that means low capillary number experiments, and hydrogen being so light can have the more diffusion and it can then have the more saturation. So those were the results for the pore-scale sample, which was small with the one fracture and the horizontal fracture, which is a big one. But then when we look at our sample B, which is more like a real network with very small aperture, we have seen there is not much difference between the methane and the hydrogen fluid distribution, and the saturation remains more or less same. So not to make a big claim, but maybe we can use these facilities for hydrogen. But yeah, these are very preliminary first results, so yeah. Now then we look at the imbibition just to see what happens to the trapping. And as you see, there are few locations where you see more hydrogen, and then there are few locations where you see more methane. And then when we look at what exactly are these slices, so when we have the higher methane saturation as compared to the hydrogen, this is the corresponding two slices for two experiments, and we have seen the aperture size is quite small for the methane when we have the methane as a higher saturation, and when we have hydrogen more, and you can see the aperture size is quite larger. So we think it's because of so what it means is in fractures, the aperture size actually controls the fluid distribution quite a lot. And also there might be slight difference between the wettability of the hydrogen and the methane. That means the contact angles would be different, so that means the fluid distribution would be a bit different. And when we look, so now this is for the sample C, which has a really big aperture, where it's like around 3 times higher than the previous sample. And you can see the drainage shows all sweep. That means the gas swept out almost all the brine, almost like 98% for the larger aperture. So it might feel it's, as compared to the 100 micron aperture, it might feel better to have the larger saturation, but when we are looking at the hydrogen saturation, hydrogen storage, we also need to take out the hydrogen. We are not just storing like a CO2. So when we look at the imbibition, we also see the recovery of the hydrogen is also quite lower in those larger aperture fractures. So what I want to say here is, in terms, when we are looking at the fractures, it's very important to look at the fracture aperture and how and the roughness of the fracture, unlike the porous media where we just can say, let's say after each cycle we are having how much recovery you can get. So just to summarize for the flow, we have seen the fracture aperture actually fracture aperture distribution controls the flow in the rock fractures, and in drainage experiments shows that different gases show more or less similar fluid distribution. And when we are looking at the trapping, we saw that the methane shows a larger trapping at first withdrawal, but it depends on, even in the same sample, it depends if your fracture is changing the width. It depends the methane is staying in the smaller fractures, but hydrogen prefers the larger fractures, larger apertures. And there is, as you have seen, if you keep increasing your aperture size, you will get really high gas saturation, but it's also difficult to recover that when you're looking at the hydrogen storage. And as I mentioned before, the relative permeability measurements are really important, but these are missing in these results. I already tried twice and they failed. So after going here, I'm going to try again, and let's see if we can get the relative permeability measurements for these, because I think whenever we are looking at the multiphase dynamics, it's very important to have that kind of measurements for upscale modeling. That's for the flow. And one last thing I want to say is that we are, as I mentioned before, we are also looking at the geochemical reactions and the microbial activity. So we are doing the batch experiments. These are not yet combined with the hydrogen flow. So what Sutkin does, we get the samples from Loenhout site in the batches, then we, at the high pressure, we put it with the high pressure and temperature conditions with the hydrogen, and maybe after a few months we'll see what reactions are happening or what microbes are produced there by doing the DNA sequencing or something like that. But if you have more questions about these, you can always talk to Sutkin, and she will have her poster next week as well. With this, I'll just tell you what's happening whenever you're thinking about the hydrogen storage. First thing is most important is look at the multiphase dynamics and have the relative permeability and the capillary pressure curves, and have the pore-scale as mentioned in the previous talk. We need to have some kind of pore-scale measurements and the displacement patterns to do the modeling. And second part is also to look at the chemistry and microbes. I think it's quite new regarding the hydrogen, and far future would be just to combine everything if anybody's interested. And thank you.
Thank you so much, Sojwal, for your interesting and concise presentation. Do we have any questions? Yes, in the back.
I have a general one. Why bother storing hydrogen underground? Why not doing it above the ground? Like, what's the advantage or the main point of it?
Is that, yeah. So because it's not economical and we don't really have enough sites, and with hydrogen, if you're just putting above ground, it's explosive, so there will be a lot of safety concerns. Currently, mostly it's stored in the salt caverns, but we just don't have enough capacity because our energy demands will increase, and we need the larger storage facilities. And about the depleted gas fields, we already have a lot of stuff going on because we used to recover oil and gas. We also use few sites for CO2 storage, and so why not use for the hydrogen? So they are just promising solutions here for now.
Losses during the storage in the underground are not significant. Could maybe compromise the economic feasibility of this?
That's what we are studying. we as in the entire hydrogen. Yeah.
Anything else? No?
Okay.
Okay, then I guess we can wrap up for the day. Enjoy your dinner and your grocery shopping, and we'll see everyone tomorrow.